What you see here is a species of ant called Temnothorax albipennis, occurring throughout the European countries. It is the rock ant which builds simple nest in the rock crevices. These small ants live in the colony of less than 500 workers with a queen. As they build their nest in the rock crevices like this, their nest area are flat and the floor area depends on the size of the colony. Whenever they need to build a new nest, they have to choose the rock crevices of suitable area that can accommodate the entire colony. It can't be too small or too large. In their natural habitat, they have been observed to choose the rock crevices of appropriate area. This means they somehow estimate the floor area of the rock crevices. How do they do it? They seem to use the technique called Buffon's needle algorithm. Let us see what is that. Buffon's needle is a classical problem in the geometric probability proposed by the 18th century French mathematician Georges Buffon. Suppose we have the parallel grid lines with the distance between the two adjacent lines being d. Now suppose we throw a matchstick of length L, that is any short line of length L, at random on these lines. There are two possibilities. The matchstick may not intersect with the grid lines as you see here, or it may intersect with any of the grid lines like this. Now the question is, what is the probability that this matchstick, that is this short line, will intersect with any of the grid lines? We can easily guess that the longer the matchstick, the more likely it is to intersect with the grid lines. Also, shorter the distance between the grid lines, more likely for the matchstick to intersect. That is, in a rough way, the probability of intersection is directly proportional to length L of the matchstick and inversely proportional to the distance between the grid lines, that is d. In fact, if L is less than d, the probability is exactly this, 2 by pi multiplied with L by d. So if we throw a standard number of matchsticks of same length on these grid lines at random, we can guess the number of intersections that can happen based on this probability. Conversely, if we know the number of intersections, then based on that, we can estimate the total number of matchsticks that has been thrown. Now, here comes the interesting thing. Instead of throwing the number of matchsticks, we can simply draw a random curve of standard length. Since this curve itself is random, we can take the curve as equivalent to the throwing of the shorter lines at random. We can take the length of each short line to be small value del L, which is equivalent to the individual length of the matchstick. Now, based on the number of intersections that this random curve makes with the grid lines, we can estimate the total length of the random curve. Now consider the question of estimating the length of the random curve. Now what if the curve is not so random like this? We can do better by randomizing the grid lines, and we can do so in the following way. Consider any enclosed region. Now instead of grid lines, we draw random lines of standard total length. Now if we draw our curve in this area, then we can estimate the length of the curve based on the number of intersections. That is the number of intersections it makes with these random short lines, given that we can guarantee enough intersections for the estimation. This technique has been in use to estimate the length of the microscopic structures like root hairs, and in stereology, which is the study of three-dimensional objects based on the slices of the object, and also in animal population estimation for those animals which leave trails like in army ants. Like they survey in random straight lines to see the rate at which they intersect with the animal trail, and based on that they can estimate the animal population. Especially this has been done now with army ants. So this technique is not new, this is well known. Now let us consider the other question. What if we keep the length of the curve to be a constant? Suppose let it be L. Now consider the number of intersections of this curve with these random lines. We have total length of random lines to be a constant, which is s, and also the total length of the curve is also a constant, which is L. Now in this case, what does the number of intersections depend on? So the total length of the random short lines is a constant and length of the curve is also a constant. So what does the number of intersections depend on? It depends on the total area of the enclosed region. Why? Because larger the area, the more sparsely packed will be the lines. If the area is smaller, then the random lines will be packed densely. So the area depends on the total number of intersections. As we have already seen with the original Buffon's needle problem, we can calculate the precise probability and the relation between these parameters: length of the curve, length of the random lines, and the area of the enclosed region. Now coming back to our short random lines, as we have seen earlier, instead of these short lines, we can have a random curve. So we can choose the random curve of standard total length. Again, the idea is that we can consider the random curve to be of numerous short lines, and again the area depends on the number of intersections between these two random curves of standard lengths. Precisely, the area can be estimated as A is equal to 2 by pi multiplied with S into L by N, where S and L are the lengths of the curves and N is the number of intersections between them. This is from the Buffon's needle calculation. The idea is that to estimate the area of the enclosed region, we can draw a random curve of standard length inside it, and then drawing another curve of standard length. Now based on the number of intersections between these two curves, we can estimate the area of the enclosed region. This is what these ants do. The worker ants, in search of the new place of the colony, visit the same place several times. Each individual ant has individual specific pheromones. It is like face recognition for the ants. Each individual ant can deploy an unique pheromone signature which it can identify. So in the enclosed area, as in the rock crevices, in their first visit, each ant move at random, laying individual specific pheromone trail of standard length. Then the ant leaves the area and again revisit. Then the ant begin to survey the region again by moving random at standard length. They can recognize when they intersect with their own pheromone trail they laid on the first visit. Now based on the number of intersections they make, they can estimate the floor area of the region. This will be done by many worker ants, and finally they have better estimation of the area, whether it is of appropriate size to accommodate the entire colony. This ant behavior was verified experimentally, and I give the paper detailing the experiments in the description. So that is the little story of these interesting insects. If you like this video, please share and leave your thoughts and feedbacks in the comments, and consider subscribing to the channel. Thanks for watching and have a great day.